Okay. Now we will define three different waves. If B0z is equal to 0, or let's say E0z is equal to 0, let's start with that one, then the electric field in this wave doesn't have a z component. The wave is propagating in the z direction, the electric field is perpendicular to the z direction. So this kind of wave we call, the electric field is transverse. So this is TE, transverse electric wave. If B0z is equal to 0, well, this time the B field is transverse to the direction of propagation. Then we call it the transverse magnetic wave. And if E0z is equal to 0 and B0z is equal to 0, we call it, what would you guess the name to be? Transverse electromagnetic wave. So these are just three different kinds of waves we can have in principle in a waveguide. Now the first thing we will prove, we cannot have transverse electromagnetic wave in a in an empty waveguide. So this is what we will prove. Well, there's nothing inside. So the waveguide that I had sketched, it's an empty waveguide. In such a waveguide, you cannot have transverse electromagnetic wave. At least either E0z or B0z should be non-zero. Unlike in space. So when we don't have these boundaries, well, both E0z and B0z can be 0, but if you put these boundaries, they cannot be both 0. Well, of course, this doesn't exclude the fact that if you have, for example, such a waveguide, in such a waveguide, you can have transverse electromagnetic waves. This is called a coaxial waveguide. Now let's see how it comes about. Look at the first equation over there. We know that E0z is equal to 0, so we have the sum of the other two terms should be 0. This is one equation we have. Look at this equation over here. B0z is equal to 0. If B0z is equal to 0, we also know that del E0y by del x minus del E0x over del y, this is equal to 0. Well, this is nothing but in 2 dimensions, not in 3, but in 2 dimensions. This is the divergence of E is equal to 0. This is the curl of E is equal to 0 in 2D. Well, we know that the curl of E is equal this tells me that the electric field can be written as the gradient of the potential, again in 2D, or E0 Ex is equal to minus the derivative of phi with respect to x, and Ey is equal to minus the derivative of phi with respect to y. If this is the case, then that equation is automatically satisfied. You see that both of those terms is nothing but the second derivative of phi in different orders, but changing the order of derivative doesn't change the result, so that difference is automatically 0. Now, if you just put this expression over there, phi satisfies the Laplace's equation. Well, what are the boundary conditions? You see, on the boundary, E parallel is 0. The parallel component of the electric field. Well, you see the potential difference between 2 points on the surface is nothing but the integral of the parallel component. So the surface is an equipotential surface. But if the surface is an equipotential surface, furthermore, phi satisfies the Laplace's equation inside, it has to be constant. Because on the boundary, phi has a constant value. But we have seen, if you remember our electrostatic course last semester, we had seen that the solutions of the Laplace's equation cannot have a maximum or minimum. They cannot have a local maximum or minimum. So phi is constant on the boundary. Furthermore, it satisfies the Laplace's equation, but that basically tells me that phi is equal to constant. But that tells me that the electric Ex is equal to Ey is equal to 0. So we cannot have electromagnetic wave. Now, how did we obtain this result? By assuming that both Ez and Bz, they are both 0. So let's say assume Ez or E0z is equal to 0, B0z is equal to 0. So once we make that assumption, we have seen that E0x should be 0, E0y should be 0, but if E0x and E0y, they are also 0, then B0x and B0y will also turn out to be 0. So this assumption tells us that there is no electromagnetic wave. So if we have some electromagnetic wave, in that case, that assumption should not be true. Either one or the other one should be non-zero.
Yani hocam bizim o conductor equipotential surface.
Okay. Be careful about terminology, how we are describing it. What we are saying is, you see, if Ez and Bz, they are both 0, we obtain these two equations. And remember, this E0x and E0y, they only depend on x and y. Well, to solve this equation, it's enough for me to assume that E0y is the y derivative of some function and E0x is the x derivative of the same function. Okay, what I call that function? I call that a potential, because I'm obtaining the components in terms of the derivatives of that function. But that function is not my electrostatic potential that we described in last semester. Okay, I will still call it the potential, but it's not the electrostatic potential. Sorry, before I pass his question. Okay, I call it a potential. Furthermore, I know that delta phi, the change between 2 points, just because of this property, is nothing but the integral of E dot dl between those 2 points with a minus sign. Of course, here the path is a two-dimensional path, and the E only have the x and the y components, the two-dimensional problem. And since I know that my surface is on my surface, the parallel component of electric field is 0. If I take my path to be parallel to my surface, this integral will be 0. So phi has the same, delta phi is 0 if I consider 2 points on my surface. That tells me that phi has the same value on the surface. Since I'm calling phi my potential, I call the surface my equipotential.
The second derivative of phi with respect to x squared, for example, is 0. So why don't we assume that phi is something like first order combination of x and y?
You say, I'm not assuming that the first derivative of phi, the second derivative of phi with respect to x is 0. I'm saying that its second derivative with respect to x plus its second derivative with respect to y is 0. The second thing I know, phi is constant on the boundary. So for example, if you take a linear function, it cannot have the same value at the two boundaries. So it doesn't work. And this differential equation, what we call the Laplace's equation in two dimensions because I only have the x and y, whatever the dimension of the Laplace's equation is, the solutions can never have a maximum or a minimum. So if it's constant over a closed surface, it has exactly the same value everywhere inside that surface. You see, why doesn't this argument work in the case of the coaxial cable or coaxial waveguide? You see, the outer boundary is an equipotential surface. Similarly, the inner boundary is an equipotential surface, but the inside and the outside need not have the same value. They can have different values. So it can start from this constant value and increase and obtain its value at the inner boundary. So I can have non-trivial solutions in that case. In such a system, I can have E0z and B0z equal to 0. Because the solution of this equation, subject to my boundary conditions, is not necessarily a constant. Now let's try to find some of the waves. Let's look at the TE waves. So you see, if you think of this in terms of some kind of a reflection and a refraction problem. Now, if you consider what we were studying in the case of an interface separating two medium. Okay, we said that, okay, if you send it with an oblique angle, you can decompose it into two components, one perpendicular to the plane of incidence, the other plane of reflection, the other, the E field, either the electric field or the B field will be perpendicular to the plane of reflection. Now here we also have some similar cases. In this case we have the wave is moving in the z direction. The electric field might be perpendicular to the propagation direction. The magnetic field can be perpendicular to the propagation direction. Well, if you send any wave, well, you can try to separate these two components. In this case, there is also the possibility that, well, making analogy with the reflection, normal incidence has both the E and the B let's say, parallel to the plane. Now, in this case, we have the propagation direction, E and B, they can both be perpendicular, or one is perpendicular, one is not, or the other way around. But it turns out that if you have this empty waveguide, there is nothing inside. In such a case, you cannot have both the electric and magnetic fields perpendicular to the propagation direction. You can have either one or the other one. Now let's start with TE waves. Now in TE waves, we know that BZ is equal to 0. Sorry, EZ is equal to 0. That is how we define this. BZ is non-zero. Now, what are the equations we have in this case? I omega B0x is equal to minus IK E0y. No, sorry, let me go further. Okay, here. E0x is equal to I over omega over C squared minus K squared times omega derivative of B0z by del y. E0y is equal to I over omega over C squared minus K squared minus omega derivative of B0z by del x. B0x is equal to I over omega over C squared minus K squared. K times derivative of B0z by del x. Well, you see, both of these are related with the derivative of B0z with x, so I can just write the second one as equal to minus K over omega E0y, if you like. And, okay, B0y is equal to I over omega over C squared minus K squared multiplying K times the B0z over del y. And this is nothing but K over omega E0x. So if I determine the electric fields, if I determine B0z, I can just straight away determine the electric fields. Electric and magnetic fields are related through this relation over there. And how do I determine B0z? Well, this is the equation that B0z satisfies. How do you solve this equation? Remember, B0z depends on x and y. Well, it just looks like the Laplace equation with this constant added. The way of solving this equation is the same as how we solve the Laplace's equation. I heard some from here, separation of variables. So let's just assume B0z is equal to some function of x only and some function of y only. So x double prime over x plus y double prime over y plus omega over c squared minus k squared, this should be equal to 0. What I did was I just put this into here and divided by B0z. So that's why I get the x and y numerators over here and nothing multiplies that one. What is B0z on my boundaries? Well, what were the boundary conditions? B perpendicular is 0. So So that is B0x is 0 on the boundary, and B0y is 0 on the boundary. Well, that means the derivative of B0z with respect to x and y is just 0 on the boundary. Right. You see, one, I already said that the perpendicular component of B0 is 0. Okay? So that is what I said. Now, in fact, I'm kind of, let's say, cheating. This is my cross-section of my waveguide. Let's say this is my x component, this is my y direction. This has a length A, this has a length B. And, well, here, B perp is equal to By. Here, B perp is equal to By. Here, B perp is equal to Bx. And here, B perp is equal to Bx. Okay?
Metalin yüzeylerini mi sınırlandırıyor?
Yes. Well, that's my bound. My volume is inside my waveguide. The boundary of my volume is the surface of my waveguide. My waveguide is just, it just extends up to infinity in the z direction. Now, the perpendicular direction to the surface at this point is this one of the B. The perpendicular direction is this one. Similarly, I know that the electric field, the parallel component of the electric field is 0. So on this side, the y component of the electric field should be 0, also over here. So let me write it in this way. At this boundary, Bx is equal to 0. At this boundary, Bx is equal to 0. Here, on this boundary, By is equal to 0. Here, again, By is equal to 0. This is from the perpendicular component of B. Or I can also say the same thing for the parallel component of E. This will tell me that the parallel component is Ey, should be equal to 0. Ey is equal to 0. Here, Ex is equal to 0. Here, Ex is equal to 0. On the boundaries, these are my boundaries. I don't yet know what is inside. Well, you see, these two conditions are not really different conditions because Bx is nothing but Ey up to some coefficient. You see the first line, Bx is equal to Ey. And this is not a different coefficient and condition than this one because Ex is equal to By up to a coefficient. So if one is 0, the other one is also 0. So these are my boundary conditions, but these boundary conditions tell me that on the boundaries, the derivatives of, you see, what I'm looking for. I'm looking for solutions of this equation. Okay, ID separation of variables. Now I can write the solution to this equation. I will call this one minus kx squared. This is minus ky squared. So x as a function of x will be some a sine kx times x plus delta x. Y will be b times sine ky times y plus delta y. And furthermore, my equation is satisfied only if k squared is equal to omega over c squared. Now, how do I determine this a, b, delta x, and delta y? And possible values of kx and ky? That is my question now. To determine those, I need some boundary values, boundary conditions. And my boundary conditions are these. At the top boundary, Ex should be 0 or By should be 0. Similarly, at the bottom boundary, at the bottom meaning parallel to the x-axis. On the sides, Bx and Ey should be 0. Those are my boundary conditions that I have to impose to my solutions in the separation of variables. You see, in these solutions, I can determine the possible values of A, B, Kx, Ky, delta x, and delta y by imposing these 4 boundary conditions. Yes? Well, both are, well, they are the same thing. This Ax is equal to 0 is the same thing as By is equal to 0. They are equivalent conditions. In this TE wave,
Şimdi hocam, manyetik alanın Z komponenti 0 dedik.
electrical, what we said is that the Z component of the electric field is 0. We are looking at the Z component of the magnetic. Okay, so let me take it from the beginning. I'm looking at this condition. Ez is equal to 0 and Bz is non-zero. We first said that we cannot assume both of them to be 0. The solution is trivial, 0. So I'm taking Ez to be 0, then Bz should be non-zero. Then I can write E0x, E0y, B0x, and B0y in terms of Bz only. So these 4 equations. Well, they tell me that B0x is equal to E0y up to a coefficient. B0y is equal to E0x up to a coefficient. Then I still have one more equation that B0z should satisfy, or Bz. Bz should satisfy this equation. Now, how do you solve this equation? Separation of variables. So we first assume that B0z is the product of 2 functions of each one being the function of the single argument. And then this is the differential equation I have. This only depends on x, so it has to be constant. This only depends on y. This is the only term that depends on y. So this has to be a constant. I call this constant minus kx squared. I call this constant minus ky squared. So this equation just becomes kx squared plus ky squared plus k squared. Or let me write it in that form maybe, to avoid any future confusion. Kx squared plus ky squared plus that k squared over here, this k squared, should be equal to omega over c squared, if I am to have a solution. Now, I can solve for x and y functions. They will have this form. This kx is that kx over there, ky is that ky, a and a, b, delta x and delta y are just some arbitrary constants that I should choose in order to satisfy my boundary conditions. Now, there are 2 issues over here. One, why did I choose a negative number here? Why not just set this one equal to kx squared? And this one equal to ky squared. Why did I put that minus sign? Well, that basically comes from my boundary conditions. My boundary conditions, you see over here. These are my boundary conditions because I have already said that the perpendicular component of the electric field should be 0. Now, the parallel component of the electric field should be continuous, and since just inside the conductor it is 0, it should be 0 on the boundary. So Ex should be 0. The perpendicular component of B should be also continuous, or 0 on the surface. So By is 0. Now, Ex and By, they are proportional to each other anyway. So if one is satisfied, the other one is automatically satisfied. And we have, on all these surfaces, we have these conditions. So that basically tells me that, you see, Ex and By, they are just derivatives of this Bz, B0z. Well, the derivative of B0z should repeat itself. It should start from 0, and after some time it should become 0. So that is a condition on the derivative of Bz, let's say. But if I assume that this x double dot, y double dot over y to be a positive number, then the solution never repeats itself, neither its derivative. So that is why, because of these boundary conditions that repeat themselves, I have to have second derivative of y over y, it has to be a negative number, so that solutions will be such harmonic functions, and since they are harmonic functions, they will repeat itself. Well, instead of the sign, let me use the cosine. Basically, I'm just changing the definition of delta x and delta y by pi over 2. Now let's try to impose these boundary conditions. First over here, Ex at 0 should be 0, or Ex at 0 should be 0. So you see E0x is nothing but the derivative of B0z with respect to y. When this is evaluated at y is equal to 0 or y is equal to b, it should be 0. Well, in terms of my separation of variable ansatz, this basically means that y prime at y is equal to 0 should be equal to y prime at y is equal to b. They should both be 0. But these two conditions are satisfied only if delta y is equal to 0. Well, if you take the y prime, it just becomes the sine function at y is equal to 0 is the sine of delta y. Sine of delta y should be 0. That tells me that delta y is 0. And the periodicity, the second condition is satisfied only if ky times b is equal to n times pi. So ky cannot take an arbitrary value. It can only take values n pi over b, n being 1, 2, etc. In fact, 0, 1, etc. So these are the possible values of ky. Well, I just repeat the same thing for the other boundary values. You see here and here, Ey is 0. But Ey, let's go back. Ey is nothing but the derivative of bz with respect to x. So derivative of bz with respect to x should be 0. When x is equal to 0 or x is equal to a. This should be equal to 0, which tells me that the x prime at x is equal to 0 should be 0, and x prime at x is equal to a should be 0. And again, if you just look at our solution for the x, it tells me that delta x should be equal to 0 and kx should be m times pi, kx times a should be m times pi, or kx should be equal to m times pi over a. These are the possible values of kx. So if you just combine all of them. So we have this solution. B0z. This is equal to some constant times cosine. Well, kx is m pi over a times cosine n pi over a. Y, this is the y component. Well, let me just put c over here. These are the possible values of B0z. B0z cannot be an arbitrary function, but it has to have this form, or of course it can be any superposition of functions of this form for different values of m and n with different coefficients. And let's see, k squared, remember k squared plus kx squared plus ky squared, this was equal to omega over c squared. Now this tells me that the k values, I cannot have an arbitrary k, but only certain values of k are possible. Let me say kmn. This should be equal to square root of omega over c squared minus m pi over a squared minus, y is b, minus n pi over b squared. Let me also call this omega mn. Now, what are some results that we can see straight from here? If omega, omega can have a discrete any value. I mean, we don't really have a restriction on omega. The only restrictions we have is for a given omega, k only can have these values. But you see, for a given value of m and n, suppose we fix m and n, omega cannot be very small. Omega should be larger than or equal to this one. Now, usually that combination we will call omega mn squared over c squared. So kmn is given by omega squared minus omega mn squared times 1 over c. There's a smallest possible value of omega for a given value of m and n. Let's look at the phase velocity. You see, this is a wave, we said that this is a wave moving in the z direction. So the phase velocity of this thing will be omega over k. This is equal to kmn. This is equal to omega over square root of omega squared minus omega mn squared, c over there. This is equal to c over square root of 1 minus omega mn over omega squared, which is larger than c. It seems that in the z direction, it is moving faster than the speed of light.
Yani borunun içindeki dalga ışık hızından daha hızlı.
Well, that is what seems to be. It is phase velocity is faster than the speed of light.
Zaten velocity diye bir şey mi?
Hayır, bu grup velocity değil ama.
İyi de hocam, iki tane farklı phase'de dalga mı var ki biz phase velocity'ye geldik?
Well, let's see what is actually happening. Why do we have that speed c is larger than the speed of light? In fact, it has a very simple explanation. If we have time. We don't have time, so we will do the details later on, but let me just sketch what is actually going on. You see, B0z is equal to Cmn times cosine m pi over ax times cosine n pi over by. But this is Cmn over 4 e to the power I m pi over ax plus e to the power minus I m pi over ax. This times e to the power I m pi over by plus e to the power minus I m pi over by. This is our b0z. And keep in mind that bz is equal to b0z e to the power I kz minus omega t. Well, what this tells me is that if you just open up these parentheses, I can write this wave as a sum of plane waves. And the wave vector of these plane waves is m plus or minus m pi over a in the x direction plus or minus m pi over b in the y direction plus k in the z direction. And k squared for these plane waves is nothing but omega over c squared. So each one of these plane waves are actually moving at the speed of light, c. But you see what is going on. This is my waveguide. The wave vector is not parallel to the z direction. You see, it has the non-zero x and y components. So what is happening is you have a wave moving in this direction, then it bounces back. This is a perfect conductor. So at the interface, the reflection is perfect. And then it just bounces back up and down. And it is confined within this waveguide. Let me draw the wavefronts. You see, wavefronts are perpendicular to these. So these are my wavefronts. My wavefronts are moving in this direction with speed c. What is the velocity of, what is the speed of this point? This point will be moving faster than the speed of light. Just imagine this way. I mean, if I had exaggerated a bit, let's say this will be my wavefront. Even if my wavefront is displayed slightly, the intersection point would have moved over here at the same time. It will cover a larger distance, this point. But this is nothing but just, if you just imagine, you take a laser pointer, you follow the tip of it. If you just move your laser pointer, the tip might move faster than the speed of light. There is no problem with that. There is no transfer of information faster than the speed of light.
Görüntü mü yani?
No, this point does move faster than the speed of light, but you cannot use that motion to carry energy or transfer energy faster than the speed of light.
There is no transfer velocity speed of light.
Transfer of information is less than the speed of light. You see, to build this waveguide, to build this plane wave, you have to send some wave first, where you will have some waves over here and nothing over here. That front of the wave will not move with c, will not move faster than c. It will move at the speed of light, or even slower than the speed of light. Because this moves at c, if you just take the horizontal component, that moves slower than the speed of light.
O zaman şunu sadece matematiksel bir sonuç.
Sure.
Fiziksel bir şey yok.
Exactly. There is nothing, no information is moving faster than the speed of light. That is the point. It appears, certain things appear to move faster than the speed of light, but because that is basically the geometry. As you said, just the mathematics. It's not the speed with which we are carrying information or we are transferring energy.
Dik ve medium'da olsa, yani
Medium.
olması.
Okay, work it out. You know the basic principles.
Ama
Nothing changes.
Işık hızını geçebilir mi?
No, you see,
Şimdi ışık hızını geçemez de pardon, yani o dalganın hızı ışık hızından düşük olduğu için ondan daha hızlı olabilir. Işık hızını geçmez.
fine, no problem with that. You can pass the speed of light in medium. We measure it constantly. The thing that you cannot pass is the speed of light in vacuum. Nothing can move faster than that. You see, if you have heard of Cherenkov light, have you heard of sonic boom? Well, basically, if a jet moves faster than the speed of sound, you hear this boom. Well, in medium, light travels slower than c. So a particle can move faster than c. So in principle, you can have the analog of sonic boom in medium for light. That is called Cherenkov light. And that is something we use to detect particles. That is something we constantly observe. You see, the sacred quantity is not the speed of light. It is c, which happens to be the speed of light in vacuum. Okay, so see you on Wednesday. So who will show up for the recitation on Wednesday?